Yes? Great. Thank you. Okay. So just as a 1-minute recap, last time we introduced the idea of ridge regression. Where we thought about the following optimization problem. Minimize over x, ax minus b squared plus lambda squared x squared, right? And we saw multiple different interpretations of this same optimization problem, right? The first interpretation that we saw was, well, we wanted to somehow reduce our sensitivity to perturbations, and we wanted to be able to be robust to these kinds of perturbations. So we wanted to make sure that the condition number of A is not too large, right? And we wanted to shift the eigenvalues or the singular values away from 0. So that was kind of interpretation 1. Interpretation 2 was that we looked at this as kind of, and why did we want to do that, right? Remember, we're going to look at the demo again briefly. But one of the things we noticed in the demo was that without the ridge coefficients, without the ridge modification, without this lambda term, the predicted values, the predicted coefficients for our polynomial were really large, right? They were coming out to be like something to the 10 to the 6 or some crazy large numbers like that. And so we said, well, what if we gave our optimization the side information that actually x is not too large? Right? We told this to our optimization. How could we incorporate this side information into our cost? And so that is what we are doing here. Remember, we're changing the optimization problem. It's important that everyone knows this. Here, we're saying we're taking the least squares and we're now writing a different optimization problem. The solution to this is not equal to the solution to the least squares problem. Okay? I got some questions in office hours about this, and I wanted to make sure that this was very clear. In general, the minimum value of this, as well as the argmin, are distinct from the minimum value that is attained by the least squares problem. Okay? Is that clear to everyone? Yes? Some nodding? Or is that unclear to anyone? Anyone have a question about this? Okay, good. So this is a different problem. It is incorporating the fact that we have this side information. Okay? We then, after looking at it as this kind of addition to the cost, this is one way of thinking about our side information. We also looked at it in the second way. We thought about it in terms of this ghost data interpretation, right? So if instead of adding this to my cost, I directly added measurements to my least squares setup, right? And I added measurements that said, well, I'm kind of confident, or I'm very confident, or I'm only a little confident that I'm close to 0 for x, okay? Everyone remember that? Yes? Okay. So I forgot to write a few lines of code in the demo yesterday, and so I'm going to go over it very quickly so that you can see what happens when we actually use the ridge coefficients. So remember where we were is we started out with this straightforward setup where we had some noisy data points. The blue points were the true points. The red crosses were the noisy points. We used least squares to estimate stuff. We got these green points. Everything was fine and dandy. This was great, right? Except then we tried to do the exact same thing with points that were spaced between 200 and 202 instead of points that were between 0 and 2. Does everyone remember that? And then bad things started to happen, right? We could, here, this is again the plot of just the real, of the true values in blue and the noisy ones in red. Remember, we're adding the same magnitude of noise here exactly as the other earlier case. It's just that we cannot visualize on this plot. That's why the red crosses appear exactly on the blue ones. And then we did least squares. We called least squares, and it looks like we do a really great job because our green dots are exactly on top of our blue dots. But when we looked at the predicted coefficients, we were not doing so great, right? We were getting pretty bad numbers for those predicted coefficients. So now what we want to do is we said, okay, well, one of the things that reasons that this is happening is that we're having these large condition numbers. So now what I said we would do is that let's now consider this least squares with a lambda penalty, right? Let's consider the objective function that we're talking about here, and let's consider, instead of the least squares solution, let's consider the ridge solution. And so here I'm adding this lambda square times identity, right? Does everyone see that? That I'm defining this least squares R, which is for least squares R for regularized, because this guy is also called a regularizer. Okay, so we did this, and we reduced the condition number of what we wanted. And now, when we do this again, what we get is, if we look at now our estimated coefficients, what do we have? We have coefficients that are not crazy large. They're actually quite reasonable. And if you look at the first order term, the most important term, right, the coefficient of x cubed, what are we getting? We're getting 3.99. And what was our true value? Our true value was, in fact, 4. Right? So at the highest order, we're doing pretty good. Our second term was negative 11. We're getting negative 10, right? 10.9, in fact. So we're getting the highest order terms pretty solidly. And our lower order terms, which were blowing up the last time, are now, quite reasonable. This is actually like the smallest term is kind of close to 0. Here our constant term is 1. Whereas if you remember last time, the constant term was what was dominating in our expression, okay? And now if you plot this even for smaller values, so now I'm again plotting between 0 and 2. I have my blue points, which are my true points here, and the green points are what my reconstruction are. They're now no longer dead on in the same way that they were for the high range of values, but they're not horribly off. They're not off by 20,000 as they were last time. They're like in a reasonable range, okay? Does everyone see this, kind of? Okay, so basically this is the key point that I wanted to get across. I'm sorry I didn't have this last calculation done the last time, but now everyone gets it, right? Okay, good. So let me stop this sharing. Any last questions about the demo? Because this is now all going to go away. Yes?
Very simple question, but like in the formula you put on the board, you put lambda and then x as the norm of x squared. But in the equation, you put like lambda times the identity matrix.
Because what am I doing, right? So if I solve this, what did we show last time? We showed that the optimal solution to this was A transpose A plus lambda I inverse A transpose B, right? So this is basically this least squares expression, but with this lambda I added, right? And what these lambda i's, we talked about the shift property, right? This basically is shifting the eigenvalues of A transpose A, and thus the singular values of A by this quantity lambda, okay? So that's why when I'm implementing it there, because I'm not writing out this optimization, right? I'm writing out the solution to the optimization. So that's why in the code I'm writing this formula, which is the argmin of this optimization problem. Okay, great. So now what I want to do is talk about a generalization of ridge. And this is called Tikhonov regularization. And remember at the end of class last time, we talked about this idea of, well, what if someone came in and kind of added a little bit of data to your experiment, to your least squares experiment, that told you something more about your experiment? So your original experiment was AX equal to B, let's say. And we drew that as you have some A, then you have some X, and then you have some B. This should be the same height as A. And we said that we could also interpret ridge as saying, well, I can have lambda I times x is equal to 0, right? Someone gave me some side information that told me that, my x was close to 0. And lambda represented their confidence in, how sure they were about being close to 0. But now, what's so special about 0? What if I had some side information that said that, well, actually, you were doing these measurements, but there was a bias term that accidentally got added, and instead of being close to 0, you're close to some other vector, maybe x naught. Could we incorporate that into this formulation? Right? I could, instead of 0 here, could I say some vector x naught? Right? That seems like a reasonable thing. What if there was other side information that you had? That maybe when you were doing this experiment, you did the first half of your experiment, maybe after you were really fresh, you were pumped, you just attended 127 lecture, you were raring to go, and you had like a great run there, you got some great data, but then you stayed up all night doing your homework, which you should never do, and then you took the rest of your data, and you were sleepy, you spilled your coffee, it was a disaster, and so maybe you had like a lot of noise in the second half of the experiment, right? Could you incorporate maybe some kind of weight matrix here that told you that, well, the first few rows of this I'm pretty confident about, but the second half of the rows I'm not that confident about? Maybe I could similarly say, well, what's so special about identity? Right? This is saying that I have equal information about all of the components of x. Maybe I have different information about different parts of x, right? Maybe instead of a lambda I here, I could have some other information, right? This is a way of now incorporating different kinds of side information. And now if I call this matrix A twiddle and this vector B twiddle, can I write a least squares problem around this? I can, right? And could I then maybe solve it in the exact same way that we solved it the last time and get a solution? And so, I might write an optimization problem such that min over x, w1, let's say ax minus b squared. So, I care more about minimizing the error in some components than in others, and maybe plus some w2 x minus x naught This is the general form of what is called Tikhonov regularization, which is basically the same idea as ridge regression, but with some more bells and whistles, right? But the fundamental core of the idea is exactly what we talked about last time, which is a way of incorporating side information into your cost function, into your loss function, so that you can actually have a better solution. Remember, our objective, I don't mean to use that, I didn't mean it as a pun, but our goal in solving an optimization problem is not to just find the optimal value of the objective. But an optimization problem is an approximation for some real world thing, right? For example, in the polynomial estimation case, we don't care about the least squares solution, we care about getting close to the true polynomial, right? Like, this is just a model. Does everyone see that? So what you're trying to do is you're trying to come close to the true reality of the real world, whether you use this model or you use the ridge model, whatever works is good. And if you need to incorporate more real world information to be able to make your stuff work better, great, do it. If it works with less information incorporated, or if you don't have the information, then do it the blind way, okay? Everyone see this? Kind of? So we're going to today's lecture is going to explore this idea of how to incorporate side information in even more detail. And we're going to start thinking about a probabilistic perspective for the first time in the class. So what if I could use probability further to incorporate the side information that I want to consider in my problem? And here I want to start off, actually, so any questions about this before I proceed? At the back, yes?
Is W1 a factor?
W1 is a matrix. So I'm thinking about it as a weight matrix that is telling me how important every row of this is, right? So I could, if I knew that the first row is really important, I could make, like maybe I would make this a diagonal matrix. I don't have to, but I could. I have design control over it, and I could weight it so that the error in the first component is really important, but maybe the error in the last component isn't that important.
I just want to verify, is that AX22
No, this is an arrow that was written really fast.
And then also, is that always the L2 norm?
Ridge regression is always the L2 norm. Excellent question. So here we talk about this as a regularization term. And this is one way of saying that x is close to 0, right? What's another way of saying x is close to 0? Instead of having the norm of x squared, what else could I have considered? Could I have considered the absolute value? The 1 norm? That's also a way of saying it's close to 0. Could I have considered the cube of the norm? I could have, right? There's lots of different ways of incorporating this kind of side information. This one just happens to be a nice and elegant way of doing it. But you will encounter many different kind of regularization terms. We often end up with doing things in the second moment because guess what? Like taking the derivative of a quadratic is easy. And we can do it nicely, and we can have nice analytical expressions. Right? And again, this is all we're doing is we're modeling the real world. As I was telling people in office hours yesterday, I think all models are wrong, but some models are useful. So we want the useful ones. If you can create a beautiful model that is very complicated, but you can do no computation on it and it tells you nothing useful because you're like just stuck doing algebra, that's not a useful model. But a simple linear one that can give you even first order predictions is very useful. Question? Yeah, this is exactly if you had some side information, right? Like, so I gave you the examples of like you spilling your coffee. That's just one example, but there's many different ways. So for example, if you're doing something that's a physical model, you might have physics-based knowledge of the underlying model. This might be one way to incorporate it. But there's a host of other ways. Okay, last question, then I'm going to move on. You could write it either way. I mean, both would be, these are all variations on the idea of Tikhonov. You could write it this way if you wanted to have different weights for this. This would also be a completely valid and correct way. Your solution would change, right? Because if I put the parentheses here, instead of x naught here, you would have a W2 x naught. It's all the same kind of thing. So if you wanted to have an exact one-to-one mapping between these two, you would have to be very careful about it. But what I'm trying to communicate is the idea. And you're going to explore a precise version of this on your homework. So you will get plenty of time to make it exactly careful. Dot your I's and cross your T's. OK, good. Let's move on. OK, so this is one kind of side information. And you've seen how I've kind of adapted our cost function to incorporate side information. But another common thing in side information is like noise is another thing that we commonly think about, right? And side information about noise or about parameter variation is often expressed and modeled probabilistically, right? So I can say that I might have some probability model that tells me something about my setup or my function. So for example, let's say I had some observations. So now I'm going to move to the XY notation for data that we've been using in the homework. since I want to think about this in a data-driven way. So let's say I have my yi, which is some g of xi plus some zi, okay? And this is my model, so every xi generates a yi. And maybe I have some information about my noise. Let's say my noise is drawn from a normal 0 sigma squared. Or let's say not even sigma squared, let's say it's not the same, let's say sigma I squared, okay? So that means that I know this relationship exists, but I know that I have some corruption by some kind of noise, okay? And this noise is modeled by a normal distribution. Remember the density of the normal distribution? So what is the density of zi? It's e to the minus zi squared divided by 2 sigma I squared divided by square root 2 pi sigma I, right? Remember this. For those of you who've forgotten your probability, good time to remember. So here I'm thinking about basically xi, yi as my data points. Okay? I'm going to make an assumption here, and I'm going to assume that I have a linear model. Okay, so I'm going to assume more specifically that g is of the function, or g is of the form, g of xi. And maybe let me consider these as vectors. But this will all work out no matter how you do it, even if they were scalars. So I'm going to consider this as xi transpose times some w. So I'm thinking of g as this linear function. And so the relationship basically between x and y is captured by this w. Okay? W is some ideally known thing, but w is essentially our model. When in the machine learning context, people say assume a linear model, they usually mean something like this. So I can rewrite this now. Instead of this g of xi here, I can write this as xi transpose times w. Okay? And I can write this now as a matrix equation, so I can write y1, y2, all the way up to yn, if I had n data points, is equal to x1 transpose, x2 transpose, xn transpose times w plus some noise, z1, z2, zn. Everyone see this? Okay. So this is like the equations that we've been seeing very often, right? This is basically, if I call this matrix x, this is y, vector y, is approximately equal to x times w, right? And how do we solve this? These squares, right? We've done this a million times at this point. We know how to solve this. But in this particular setup, is there something else we know that least squares isn't going to take into consideration? What do we know here that we don't know in the least squares setup? We know the density of the noise, right? We know something more about the noise. We have side information. We might know, for example, that the first two observations were really noise-free because they have very small sigma i's. But the last 5 were terrible and have giant variance. Okay? So least squares would not take that into account, right? So one way to make least squares take something like that into account would be to introduce some kind of weight matrix here, like this W, right? And do some kind of weighted least squares. Okay? But as people were asking, how do you find this W? What is the right W? How would we even know this? Or maybe there's a way of probabilistically solving this to be able to get a different strategy for estimation, right? This is just one strategy for estimation, but maybe there's others. Everyone with me on what we're trying to do? So the solution we're going to explore is maximum likelihood estimation. Okay? What does this mean? We have these pairs of data, x, y. We want to find that W that makes the observed data most likely. Okay? So in particular, we want to consider the density, the joint density of all of our data points. So I'm considering the joint density of f of, what is the probability that my first observation is y1, my second observation is y2, my nth observation is yn, conditioned on w equal to w naught. What is the w? Like basically for every choice of w, I have some set of observations, right? I have these x's, I know what the y's are, and I know what the corresponding x's are. Every choice of w induces some density on these particular observations, right? And I want to find that w that maximizes this density, okay? So if I wanted to find this, right, this is an optimization problem, what would I be looking for here? Which w do I want to find? The argmax, right? I want to find the argmax of this over w naughts. Everyone see the problem formulation? This estimation, you've probably seen in your probability class, but if you've forgotten, this is called the maximum likelihood estimator because it's saying what is the unknown that makes your data most likely. Okay? Yes?
Strictly speaking, if dealing with continuous variables, is it like density?
So the question is, since we're dealing with continuous variables, are we talking about density? So yes, we're talking about the maximizing the density in the case of continuous random variables. Yep. Which is why we're writing an F here and not a P, because we're not thinking about probabilities, right? This is a Gaussian density, not a probability. To get a probability out of this, you'd have to integrate. Question, yes?
Don't we kind of have like an initial belief of what W could be from our prior assumptions though?
So question is, what if we also had some information a priori that told us something about W, right? Well, maybe we could incorporate it, maybe we couldn't. We'll talk about it in the next section of lecture. But first, we're going to assume that we know nothing about W, and we're going to try to solve this in the maximum likelihood style. So this is something in probability you can have, you can either think about things with a prior or without a prior. The way of doing estimation, if you assume a prior, is a Bayesian way of using maximum a posteriori or map estimation, which we're going to talk about next. But right now, we're talking about maximum likelihood estimation, which assumes that we don't necessarily have a prior on W, but we have a prior, we have some information about the noise. Yes, Shrestha.
Will this give us the same W as doing the least squares the linear model of the problem that we had before?
It might, but it might not, right? We don't know that yet. But you might have a nice answer to that question. Yes, question?
You mentioned earlier that like one way to kind of solve like the original problem that we're doing is like maybe picking W that's like in the
Tikhonov regularization.
Yeah, picking W that's like inversely, like inverse of the size of like the variance.
that might be one way, but you could take, would you take it inverse of the variance? You could take it inverse of the standard deviation. There's all these variations that you could do to incorporate this side information.
Well, does that give us, why would the maximum like give us something more?
So we don't know exactly. So all these questions are like, what is the answer? What is the answer, right? So we're going to get to that, and we're going to compute this. And as you're all thinking, given the theme of these lectures, we're probably going to get something that's kind of nice. So we're going to get there, but both of your questions are prefetching the next 10 minutes of lecture, so they'll be answered in 10 minutes. Okay. Good questions. Anything else? Okay, so let's do this calculation, right? So I have this. I'm assuming that each of my noise points, so let me just say this. I'm assuming that these are all IID, which means independent, identically distributed. And this independence is something I'm going to use to process this density, right? So I have y1, y2, yn. Each of these, I know that every yi has this linear relationship. I know that yi is equal to xi transpose w plus zi. Okay? Remember here, I know xi and yi. I do not know zi. And w is what I want to estimate. So since these noises are all IID, these yi's are all independent of each other, right? One yi is not, these noises are basically all independent. So I can basically write this out as a product. All these yi's are independent. So I can write this as the product of I is equal to 1 to n, density of yi is equal to yi, given w is equal to w naught. Because the only way these y's are connected to each other is through this w, but I'm conditioning that out. So I can write this as this product. So now what remains to be understood is this conditional density here. So why don't you start working that out while I'm erasing the board? Oh dear. So how am I going to compute this f of yi equal to yi given conditioned on w is equal to w naught? How can I write yi in terms of this w naught? What do I know about the relationship between y and w? I know exactly this linear relationship, right? I know that yi is basically equal to xi transpose w naught plus zi is equal to yi, given w is equal to w naught. Right? The fact that I observed that my ith observation is yi means that this equation had better hold true under my model. Okay? I can just rearrange this. And so this is the density now. I keep writing these vectors on zi's. These are not vectors. I would write this as zi is equal to yi minus xi transpose w naught. Just rearranging, right? If that equation is true, it's the same as this equation being true. But now, can I write out the density, this density explicitly? What is this density? We know this, right? So I can just use the formula for the Gaussian density. And so this is e to the negative yi minus xi transpose w naught whole squared divided by 2 sigma I squared divided by square root 2 pi sigma I. Okay? We good here? Just plug and chug. So if I have this expression for each one of these, I can write this product as the argmax over W as the product of e to the minus yi minus xi transpose W naught whole squared divided by 2 sigma I squared divided by square root 2 pi sigma I. Right? Now in this expression here, we want to find the argmax. We want to find that W naught that maximizes this. Does this denominator, is this going to matter here? Not dependent on Wi, right? These sigma i's are what they are. This product is going to basically fall out, and I'm going to be able to rewrite this as I can have this product here, and I can remove these guys and pull this out of the product. So I can have 1 over square root 2 pi raised to n, and then product of all of my sigma i's, right? I can pull this product out. Okay? And so this argmax is really now applying to this thing. Okay? Does everyone see that? So now if I'm trying to find, let's say, the argmax over W of some f of W, some general function of W, okay? I want to find that W that maximizes f of W. Can I do any transformations on this function that would preserve this? We've kind of done this. For example, if I wanted to find the max over x of, let's say, ax minus b, 2 norm, okay? Can I? We can square it, right? So if I, excellent. So if I want to find this argmax, if I want to find the x that argmax is this is equal to the x that maximizes the square of this. Does everyone see this? Yes? So can we do something similar in this case here? Do we want to be squaring this argument to make it simpler to process? Not really. But what might be something that we would want to do? Take logs, right? So I could say that this argmax is the same as the argmax of log of f of W. And why is this true? Why can I do this? Because log is an increasing function, right? So if I was to draw out the log function as a function of W, so if this is my W, what does log look like? Log looks like this, right? Well, not like it flattens out, but right? This is what log looks like. As log approaches 0, this is asymptotes towards negative infinity, right? Log 1 is 0, right? So this is an increasing function. So basically, if I was to increase f of x, what would I do to log f of x? I would strictly increase it, right? If I was to decrease it, I would strictly decrease it. So because I have this monotonic increasing relationship, the argument that maximizes f of x is the same as the argument that maximizes log f of x. And this is true if I had any increasing transformation. Does everyone see that? And so these kind of tricks are things that are going to start being useful for you as you solve different optimization problems. Yes, question?
Yeah, so when we talked about the norms and then square it just to make minimizing the square of the norms the same, that assumption there was that the norm is always positive.
So here we were also using the fact that by squaring this, we are always having an increasing function. So it's, we're using the fact that it's an increasing, strictly increasing function. Okay. So what we're going to do here is we're going to take logs. Remember also, one important thing. Max, terrible color. Important to note. Max x ax minus b is not equal to the max ax minus b whole squared, right? Because now that you care about the actual function value, what is attained. Only the argmaxes are equal, okay? Important to remember. Good. The same thing is going to hold true here. What can I do? I can now take logs of this whole thing. I don't have to care about this thing, because the argmax doesn't care about this thing. So I can write this as argmax over W naught of log of, maybe I will take one more step. Before I take logs, I'm going to just do one other step that will make my life easier. I have a product of exponentials. This is e to the x1 times e to the x2. So I have e to the x1 times e to the x2. What is this equal to? E to the x1 plus x2, right? So I can write that at e to the negative, or I'll just write it as exponential, minus sigma yi minus xi transpose w naught whole squared divided by 2 sigma I squared. Okay? Equal to argmax over W naught of the log of this, so argmax negative yi minus xi transpose W naught whole squared divided by 2 sigma I squared. Okay? And dropping constants. Anyone can see where we're going by now? All those least squares aficionados? Okay. So, what is this thing? What do we have? This is a sum. So if this is an argmax of a negative quantity, can I write this as an argmin? So this is the argmin W naught of sigma yi minus xi transpose W naught whole squared divided by 2 sigma I squared. Okay? But what is this? Is this almost exactly like our least squares cost? Right? Remember, our least squares setup, what is our setup? You have basically ax minus b. So x1 transpose w minus y1 squared plus x2 transpose w minus y2 squared. This is exactly our least squares cost, except you're scaling it, right? You're having a weighted least squares. And what is the weighting? It's this quantity, right? So this is the same as argmin over W naught, 2 norm of basically, let's say, x W naught minus y weighted by some matrix S. And how am I going to weight this? I'm going to write it as 1 over 2 sigma 1 squared, 1 over 2 sigma 2 squared, 1 over 2 sigma n squared. Yes, question?
Didn't we assume that all the CIs are IID though? So that's the same.
Good point. So if we do, fair enough, I shouldn't assume they're identically distributed because I'm assuming the sigmas. When I meant identical, I was just assuming the Gaussianity. Let's just say they're ID, just to make the problem interesting so that we have different sigma i's. But if all of these sigma i's were equal, what could we do? Would this weighting even matter? This would be exactly least squares, right? If these were all exactly IID and all of the variances were equal, you would get exactly least squares. If you were not identical, if you have different sigma i's, basically this is telling you, by weighting, you're weighting basically by the inverse of the variance. This is telling you, well, place more, be more careful about the error on some terms where your observation has low variance, and be willing to have larger errors where your observation has larger variance. Right? Yes, question?
Would that be square root of 4 over?
Yeah. You would write this. Thank you. Because I want to square the norm here, thank you for that. Someone else, if there's another question. If not, I'll come back to you. Other questions? Okay.
Do we have to include the 1/2?
Do we have to include the 1/2 in our formulation? No, right? Won't matter in terms of finding the argmax. Yes?
Could we pre-process the data and standardize it with pre-processing?
Could we do some pre-processing to make these noises equal? You might be able to do that, yeah. But you'd have to be careful about how you do it. Though this is easy enough computationally that there would be no reason to really do it in this specific setup. Yes?
If we're not including the 1/2 in the formulation, then can we just write S as just 1 over sigma I?
Yes, if you're not including the 1/2, again, because we're only caring about the argmin and not the actual min, The 1/2 doesn't matter. It's just a constant that'll scale everything up and down. Yes?
Just like tying it back to like in like real world use cases, when do we like add like noise into our data? Like,
So when do we add a noise? Okay, great question. Why are we adding a noise into our data? Who would do that, right? Like, yes, you've already labeled me as crazy, but this is really crazy. Why would you add noise to your data? No, so the thing is that we're not actually adding noise to our data. We're creating a model that represents our data. So what I mean when I have this model is I'm saying that I believe that the true relationship might be, I have some g of x gives me y true, okay? But if I could measure y true, I would, but I can't. So as a way of acknowledging the fact that I cannot measure y true, I am acknowledging it by saying my yi is my y true plus some noise. Okay? Does that make sense? Okay.
This is going to work with different kind of, with a bunch of different noise, right?
Would these work with a different bunch of different noises? Okay. So if you I'm assuming you mean different densities here.
Yeah.
So if I had different densities, maximum likelihood estimation always works. This will always work. This nice simplification that says that you can have the least squares estimate be equal to the maximum likelihood estimate, that relies on this Gaussianity assumption and the linear model assumption.
By the calculator is the square of the exponential, right? I mean, I can use a different kind of...
So there, yeah, so as long as you can reduce that to being of this form, yes, so there's other densities that could work, but this will not be true for every density. For many densities that are variations on this, you could get this. But in general, this might not be true. Yes, last question. Okay, no, I'll take you because you haven't asked a question yet. But
Just like picking back off that question though, like using the intuition from the first part of class though, should it work for every like symmetric type of estimation where
it may or may not. You would have to basically make sure that you have this least squares formulation. But you could generalize it to other densities as long as you can reduce it to this. But basically, the only place that we're really using this Gaussianity is right in this spot, right? You could, all of this product formulation, everything else will work out the same. Last question.
So it's almost, okay, tell me if I'm understanding this correctly. It's almost like we're normalizing our data, right? So that we're kind of like bringing the variance to an equal level?
Yes, basically that is what is happening. Basically what you're saying, well, yes, you can look at it that way. That is correct, actually, which connects to the question that was asked up here in the front, which is that you can think of this as you're basically scaling each of your equations to say, well, I want to have all of the variances to be normalized to be exactly equal to 1. So that is a perfectly valid interpretation. Thank you for bringing that up. And I didn't realize that that question was asking the same thing, but you're absolutely right, that you can interpret this as just scaling all of your data to have normalized variance. Okay, great. So now we've done maximum likelihood estimation, and we now know how probabilistic assumptions can match our linear algebraic perspectives on the matter. But now we're coming back to the question that was asked up here, which is, well, you said you knew something about the noise, and you're trying to estimate W, right? W is your unknown. What if you knew something about W itself? Like in the case of ridge, right? In ridge, we're saying, well, our W, our unknown vector, we said, oh, maybe it's close to 0, maybe it's close to some other known vector. Well, what about if we had some kind of prior that was of a similar form, right? So what if we have a prior on W? Okay? Now we're going to use maximum a posteriori, or MAP estimation. Okay? We're going to assume the exact same model, yi is equal to xi, suppose wi plus zi. And let's assume that zi, again, are the same, normal 0 sigma I squared. And let's say wi. Now, I know that every entry of w is distributed according to normal mu I, comma, rho I squared. This letter is called rho. Okay? And I can write this, I want to write this as multivariate Gaussian. I would write it as w is distributed normal according to mean mu. And variance, I'm just going to call it sigma w. Okay? So I'm going to write this in the multivariate normal style, where my sigma w is now basically these covariances along the diagonal, or these variances along the diagonal, the covariance matrix. Okay, so what this is representing is that each of the entries of wi they have 0 covariance, so wi is not correlated with wj, but the variances of each of the individual terms are rho 1, rho 2, rho n. Okay? Everyone see that? Okay. What should I erase? Question? Speak up, sorry.
What's the last term? It's xi transpose.
W plus, sorry, this is just me interchanging cursive writing and zi. Yes? What's an example where you would have a prior on W? Okay, let me think if I can come up with something reasonable on the spot. So for those of you who have taken 16A, you do the imaging lab at the beginning, right? For those of you who haven't taken 16A, basically the first lab, it talks about medical tomography. And what you're trying to do is you have an image, and you're trying to, reconstruct it through repeated measurements. And the model that you set up is that you set up every pixel as a variable. You take different linear combinations of this pixel, and by taking multiple measurements, you then invert the matrix, or you use something like least squares to then reconstruct what the actual image is. Everyone kind of have a sense of what we're doing? So your unknowns, this is like in this case W1, W2, Wn would be the pixels of your image, or here WNN if you're thinking about this image as a square. Now you might have a reasonable prior on what these pixels are. So for example, if you're doing MRI for my shoulder, shoulders look a certain way, right? So you kind of know that you expect to see some bone in there and some muscle in there, and you have some sense of where these are. So you might have a sense for what values these pixels are going to be. And so that's something that you would incorporate into a prior in the model. Okay? Does that help? Yes, question? No? Okay, great. Good. So now what we want to do is we want to find what is the most likely W given the data, which is a different question from what we asked last time. We are asking, what is most likely W given data y1, y2, not yn. Okay? And so now what we want to find is we want to find the argmax over W of, now we want to maximize the density of W given our data, let's say capital Y is equal to little y. Okay? What we were looking at in maximum likelihood was the flipped, right? We were looking at the data conditioned on W. Now we're saying we want to look at what was the maximum, what is the best W given what we have observed. Okay? This is the difference between maximum a posteriori and maximum likelihood. Okay? But now remember that I can write f of W given y equal to y. I can expand this out using Bayes' rule, right? And Bayes' rule tells me that I can write this as f of y equal to y given W times the density of W itself normalized by the density of y, right? Everyone remember Bayes' rule? Now when I'm doing this argmax here, this guy doesn't depend on W at all, right? Your data is what it is. Its density is what it is, right? It was very likely data. It was very unlikely data. You can't do anything about it. Like the die has been rolled. You've observed what you're going to observe. So when I'm writing this argmax, I can basically ignore this as a constant, right? So I can write this argmax as f of y equal to y given W, which is something we just spent a bunch of time computing, times the density of W itself, right? Everyone with me? What did we do last time for this? Over here. Did I erase it? Of course I erased it. Because these y's were independent, we said that this joint density, right? Remember this, I'm writing this as a vector y, but really I can just write this. This is the same as f of y1 equal to y1 and y2 equal to y2 and so on, right? Yes? So I can just write this as a product, right? The same way we did last time, because all of these are independent, conditioned on this W. So this is now the argmax over W of the product of f of y equal to yi given W. I is going from 1 to n times f of W. So the last time we were looking at just this, right? Now because we have this prior, we have this extra term around. Everyone see that? Good. So what does a good lazy engineer do when you see a computation that you've already done before? You use it. Okay. So I'm not going to do out the same calculation that we did last time. Oh, actually, I can use this space here. Very nice. So this I can write out as basically the argmax. Actually, no. Never mind. argmax over W, the product exponential of minus yi minus xi transpose W whole squared divided by 2 sigma I squared. This whole thing divided by square root 2 pi sigma I, right? That's this first term. I'm just copying from what we did last time. And now I have to deal with the density of this W, right? But what do we know about W? What is the prior on W? Do we know exactly what this is? Do we have an expression for it from our model? This is just the multivariate Gaussian density, right? So I can write this as exponential of minus W minus mu transpose sigma W inverse W minus mu divided by square root 2 pi to the n times the product of all of the rho i's. All I've done here, for those of you who are wondering where this expression came from, this is just the multivariate normal density, right? Remember, when I write out just the density of, if W was just a scalar Gaussian, the density of it is e to the minus x minus mu whole squared divided by 2 sigma squared divided by square root 2 pi sigma, right? This is the multivariate generalization. Everyone see this? So I have the inverse of the covariance. This is a quadratic term. And I'm dividing by the fact that there's n of them. OK? This is just the same exact, like it's basically the multivariate normal formulation. Question?
Why is the square root term inside the exponential?
Why is the square root term? Oh, sorry. Yeah. That's obviously not. Was that your question? Okay. Yeah. Yes?
So, why are we using like the sigma matrix here? Like, is this diagonal? Can we do the same thing from earlier and use like the
Yeah, you can. There's many ways. This is the most compact and most efficient way of writing this. There's like, it's just the easiest way of doing it. There's many ways of doing algebra, and this is one way of doing algebra. Okay, good. So now here, what are the things that we can basically, that we care about, and what are the things that we're going to discard? So we have a product of these terms, and then we have this exponential, right? What are the constants that are not going to make a difference for our argmax? These guys aren't going to matter. These guys aren't going to matter, right? And now I have these two exponentials. So can I write this now as a sum? So I can write this as argmax over W, the exponential of sigma I going from 1 to n, yi minus xi transpose W whole squared divided by 2 sigma I squared. And now what am I going to add to it? Plus, I can just add this term, right? This is a product of exponentials multiplied by another exponential. So it just gets added to this. minus yes, thank you. Now I can do the same trick, right, that I did last time. Do I care about the exponential? Can I just take logs? So I'd lose the exponential. Okay? Can I lose the negative signs and write this as an argmin? Okay. This we already know how to write in terms of our compact data matrix. This is argmin W S X W minus Y whole squared, right? Plus, can you write this as a norm squared? This is something, symmetric matrix, something. So if I can write sigma inverse as square root sigma inverse times square root sigma inverse. This you did on the homework problem, right? That if you have a symmetric matrix, you can always write it as a decomposition. You can have a matrix square root for a symmetric matrix effectively, right? So this decomposition exists because our covariance matrix is always symmetric. So I can write this as the norm squared of square root covariance matrix inverse W minus mu. What does this look like? If mu was 0, what would you get here? It would get ridge regression, right? But if you had some other information, would it also get incorporated? You'd be in the Tikhonov regime, right? And now this probabilistic model is a precise way of understanding exactly how to choose these W1s, W2s, or even the lambda parameter in the ridge case, based on what you might have as prior information. So the more confident, for example, this information about these covariances or the variances would inform how you would choose your lambda in the case of ridge. So for example, if you had some rows that were really large, right? These rows are the variances of the W's. It would basically say, like, don't care too much about making sure that W is close to mu in those components. Right? But if rho is pretty small, then you would put a high weight on making sure that W is close to mu on those components, for example. I see some like general question mark faces, so questions. Yes?
I don't understand why we are taking care of S, because, I mean, in theory, the argmin is independent of S matrix, right?
I'm not sure I understand the question.
Yeah, probably before. Actually, it's the same here.
Yeah.
I mean, if we have to compute the argmin of just the first part, right?
Uh-huh. So S here, so here I'm thinking of these sigma i's as distinct. If they were all identical, then S would make no difference. But here I'm thinking of S as 1 over 2, or even sigma 1 squared, 1 over 2 sigma 2 squared, 1 over 2 sigma n squared. So what S would allow me to do is if I had a lot of confidence in my first few equations, if these variances were very small, and these were very large, S would allow me to incorporate that into my cost. So if all of these sigma, if my data was truly identically distributed and it had the same variances, then I wouldn't need to write this S. But if they had distinct variances, then this S would tell me which data points are more reliable and which ones are not. Does that make sense?
But in theory, I mean, in theory for solving the equation, S doesn't matter, or doesn't matter.
In theory for solving, no, it,
I mean, the minimizer is always W that minimize the right part.
no, this would affect your solution as well. Yeah. Yes, question?
Is there a reason why in the S matrix we have to divide by square root of 2, but in sigma matrix don't divide by square root of 2 in diagonal?
I'm not sure what you mean, but it might just be that, like, I defined S differently in the other case. It'll be all consistent. I'm not sure I understand your question.
I think like S has like less weight than like the square root of sigma W inverse. And that's not like
Oh, you're saying that sigma inverse, I see. You're saying that these are relatively, I see. That's an excellent question. That's an excellent question. I might have missed a factor of 2 somewhere. I'll get back to you on that. Send me an email. Other questions? Yes? The question is, in practice, how easy is it to know or not know any of these variances? And it really depends on how you're setting up your experiment and your model. So in a lot of machine learning contexts, you actually know nothing about your data. You just pretend that it's distributed according to some nice Gaussian model. And if you maybe happen to know that something has a higher variance and something has a lower variance, you just blindly incorporate it in your model and hope for the best. And part of the skill in using these techniques is choosing the right model. So if you assume a wrong prior, you will get terrible results. Exactly, so wrong variances are a way of assuming a wrong model, and that would be bad. You would probably get something reasonable, which is why, for example, if you know nothing, maximum likelihood is the way that you would often go, because it acknowledges that you know nothing. Okay, thank you. That's it for today. See you next class.